Hey everybody, thanks for coming out. We're just opening up, so I'm going to give it another minute to let people start filling in, then we'll get started. All right, it looks like we got about half the people that signed up are in now, so I think
Great.
I don't want to hold you up any too much longer, Mitch. So let you get started. But I first want to give a shout out to Don Doherty, our webmaster, for doing all the back end work to get all of these Zoom webinars set up and all those emails that go out. So big thanks to Don, and a big thanks to Justin Wong and the YEA team for putting together the spring conference virtually like this. Yeah, so without taking up any more time, Mitch, take it away.
Thank you very much. Well, thank you everyone for joining today. I hope that sharing your time with us today will be value added for you. And we're going to be talking about a great topic today of energy recovery. We'll go over a quick refresher of a lot of the basic topics that you see in the engineering world today, and then we'll go through some code requirements and a lot of application considerations. The application considerations will take advantage of probably the bulk of our time today. With that, I'll get started. My name is Mitchell Kelly. I'm an account manager with Train Technologies here in Chicago. I'm also the ASHRAE Illinois Chapter CTTC co-chair. Let's jump right in. So our agenda today, like I mentioned, we're going to go through airside energy recovery first. We're going to talk about why one might look into this solution and what code implications are involved. We'll look at the different types and styles of airside energy recovery in the market today, and a lot of application considerations like frost protection and limited capacity, things like that. We'll also jump into waterside energy recovery, also known as waterside heat recovery. We'll talk about why you might use this sort of a technique in your designs, what code implications are involved, and the different type styles and application considerations for that. We'll also have some bonus topics at the end, talking about heat recovery in both VRF systems and water source heat pump systems. But with that, we'll get started with airside.
And hey, Mitch, just as you're getting started, I want to remind everyone that we do have the Q&A open. So if you have any questions that come up, please submit your questions in the Q&A, and you can upvote questions as you see them.
Perfect. So first, let's discuss why we need outdoor air at all. In an effort to improve indoor air quality, buildings are ventilated with outdoor air to prevent the buildup of contaminants that are generated indoors. In most climates, this outdoor air imposes a major load on the HVAC system, unless you live in a nice place like Seattle, but here in Chicago, definitely imparts a load. This increases monthly utility costs by requiring the system to heat, cool, humidify, and dehumidify the outdoor air. This load can be reduced significantly by transferring energy between the outdoor air and the built-in exhaust air streams. The illustration shown here shows an air-to-air energy recovery device being used to precondition the outdoor air system. The air-to-air energy recovery refers to the transfer of sensible heat or sensible and moisture between two or more air streams, or between two or more locations within the same airstream. When it's hot outdoors, energy from the outdoor air can be rejected to the cooler exhaust air. But when it is cold outdoors, energy can be recovered from the warmer exhaust air and transferred to preheat the outdoor air. Next, we'll start with an easy answer to why one might use airside energy recovery. Local codes such as ISCC 2018 and others mandate the practice given certain circumstances. ISCC 2018, which is based on ASHRAE Standard 90.1 2016, requires the use of exhaust air energy recovery devices when an individual fan systems meet the code conditions shown in the table here. Naturally, in facilities that operate greater than 8,000 hours per year, the energy recovery mandates are more restrictive. Additionally, you can see here that in more temperate climates, the requirements for energy recovery are less restrictive. As an example, let's look at the impact of using a sensible energy recovery device for outdoor air preconditioning. All sensible energy recovery devices perform identically on the psychrometric chart, only their effectiveness differs. Here's a coil loop installed to precondition the outdoor air. During the cooling season, sensible heat is removed from the outdoor air and transferred to the exhaust air. During the heating season, sensible heat is transferred from the exhaust air and used to preheat the entering outdoor air. The coil loop in this example transfers heat between about 10,000 CFM of outdoor air and 7,000 CFM exhaust air. At these unbalanced airflows, the effectiveness of this system is 56%. So let's look at how the sensible energy recovery device looks on the psychrometric chart. The cooling design condition for Jacksonville, Florida is 96 degrees dry bulb and 76 degrees wet bulb. We mark it here as OA. The air leaving the occupied space picks up sensible heat from the roof and the lights as it travels through the return air plenum and returns to the central air handler at 78 degrees. We'll call this EA here. The coil loop pre-cools the outdoor air to about 89 degrees. We call this OA prime. This heat is transferred to the exhaust air leaving the building. This reduces the cooling load by 6.5 tons in this case, which lowers operating costs, but maybe more importantly allows the cooling plant to be downsized. The first cost savings associated with this downsizing can often be used to offset the cost of the coil loop itself. Now let's look at winter operation in Jacksonville. The heating design condition is 31 degrees dry bulb. Again, we mark that as OA. And the air from the space returns to the central air handler at 70 degrees, again marked here as EA. Sensible heat is removed from the exhaust air and used to preheat the outdoor air to about 48 degrees, again shown here as OA prime. This reduces the heating load by 183 MVH, again lowering operating costs and allowing the heating plant to be downsized. So let's look at a predominantly heating climate, such as Minneapolis, Minnesota. At the cooling design condition of 91 degrees dry bulb and 73 degrees wet bulb, again marked as OA here, the OA is pre-cooled to about 86 degrees to OA prime, and it reduces the cooling load by 4.6 tons. At the heating design condition of -16, the outdoor air is preheated to about 7 degrees OA prime, a heating load reduction of 245 MVH in this case. A key thing to notice in this example is that the air passing through the exhaust side of the coil loop reaches the saturation curve, meaning that moisture condenses on the coil surface. The small amount of latent heat, which is the latent heat of condensation, does add to the total quantity of heat transferred to the outdoor air. However, no moisture is transferred, only sensible heat. The moisture falls into the drain pan on the exhaust side coil. Now, moisture condensing on the exhaust side coil can present a problem. If the coil surface temperature drops below 32 degrees, this moisture will form frost, eventually blocking the flow of air. To prevent frosting, the entering outdoor or exhaust airstream can be preheated, or the capacity of the energy recovery device can be reduced. In this example, the coil loop uses a three-way mixing valve to mix relatively warm fluid leaving the exhaust side coil with the colder fluid returning from the outdoor coil. This reduces the capacity of the coil loop, preventing the exhaust airstream from reaching the frost condition. Alternatively, a variable speed drive on the pump can be used to reduce heat transfer and prevent frost. The temperature threshold at which frost begins to form depends on airflow, entering conditions, and device effectiveness. Now, let's look at the impact of using a total energy recovery device for outdoor air preconditioning. Here is a total energy wheel installed to precondition the outdoor air. During the cooling season, this desiccant-coated wheel revolves slowly through the outdoor and exhaust air streams. It removes both sensible heat and moisture from the outdoor air and rejects it to the exhaust air. During the heating season, the wheel recovers both sensible heat and moisture from the exhaust air and transfers it to the outdoor air. At these unbalanced airflows shown, the effectiveness of the wheel is 82%. So again, let's look at how this looks on a psychrometric chart. Now, you need to use a wheel selection program for this, but when you use a wheel selection program, you can see that cooling design conditions in Jacksonville, the wheel cools and dehumidifies the air to about 86 dry bulb and 69 wet bulb. Both sensible heat and moisture are transferred to the exhaust air, resulting in a, let's see, how much does reduce? Results in about 22.5 tons reduction in cooling load in this case. Again, this lowers operating costs and allows the cooling plant to be downsized. At heating design, the wheel transfers sensible heat and moisture from the exhaust air to the outdoor air. The sensible heat recovered raises the dry bulb temperature of the OA, resulting in a reduction of heating load of 242 MVH. Additionally, in this case, the moisture or latent heat transferred from the exhaust air humidifies the entering outdoor air. If the HVAC system includes mechanical humidification, this results in an additional latent load reduction of 62.8 MVH. Using the same total energy wheel in Minneapolis, at cooling design, the wheel cools and dehumidifies the outdoor air to about 84 dry bulb, 68 wet bulb, and this reduces the cooling load by 16.5 tons in this case. But if we look at the heating mode, similar to the coil loop, when the wheel surface temperature is below the dew point of the return air, moisture will condense. If the surface temperature of the wheel drops below 32, this moisture will form frost. The outdoor temperature at which frost will form on a total energy recovery device is lower than the frosting temperature for a sensible energy recovery device. This is because the wheel removes moisture from the return air, keeping the condition of the air away from the saturation curve. At heating design in this example, a preheat coil is used to warm the entering outdoor air up to the frost threshold temperature, which is about 1 degree in this example. The wheel further heats the air to about 40, resulting in a sensible heating load reduction of 424 MBH. Again, if mechanical humidification is used, this results in an additional latent load reduction of 130 MBH. Of course, when investigating the first cost savings due to the downsizing of cooling and heating plants, you need to consider the impact of energy recovery device on the first cost of other system components. The addition of an air-to-air energy recovery device for both outdoor air preconditioning or sensible air tempering adds static pressure drop to both the outdoor and exhaust air paths. This requires more fan energy and possibly larger fan motors to overcome the increased static pressure drop. It may create even the need for a powered central exhaust fan where one was not required before. It is important to note here that ASHRAE 90.1 and ComCheck allow additional air pressure drop credits in the fan motor limitation section to overcome additional ERW pressure drop and still remain in compliance when using these devices. With the exception of coil loops, air-to-air energy recovery devices require that most of the building exhaust air be routed back to a central location so that the exhaust air stream is adjacent to the entering outdoor air stream. This may require more ductwork than a conventional layout. A detail that is sometimes overlooked when using an air-to-air energy recovery device for outdoor air preconditioning is to provide a method to modulate the capacity of the device. It is required to prevent the overheating of the supplier during cold, but not extreme weather conditions. In this example, a total energy wheel is used to precondition the outdoor air in a mixed air VAV system that supplies a constant 55 degrees dry bulb. At this condition, the outdoor dry bulb temperature is 40 degrees, and the supply airflow of the VAV system is 18,000 CFM. If the wheel was turned off, the mixed air temperature would be about 53 degrees. This would require the heating coil to operate in order to heat the mixed air to the desired 55. Operating the wheel at full capacity, however, would heat the entering outdoor air to 64.6 and would result in the mixed air being overheated to 67 degrees. The cooling equipment would then need to be operated in mechanical cooling in order to cool the supply air to the desired 55. Now, reducing the capacity of the wheel by modulating the exhaust side bypass dampers in this case avoids overheating the supply air. Operation at a partial capacity, the wheel heats the entering outdoor air to only 43 degrees, which results in a mixed air temperature of 55. No mechanical heating or cooling is required in this case. The capacity control shown here could also be accomplished via VFD on the wheel, but the minimum VFD speed could come into play during a mild day, such as shown here, causing mechanical cooling or heating to be required to obtain exactly 55 degrees. As described earlier, moisture condensing on the exhaust side of the device will begin to freeze or frost if the surface temperature of the device drops below the frost threshold temperature. Any air-to-air energy recovery device used to precondition outdoor air is subject to frost buildup during very cold weather. The outdoor temperature threshold at which frost begins to form depends on airflow, entering conditions, and device effectiveness. This frost threshold is much lower for a total energy recovery device than it is for a sensible energy recovery device. This is because the total energy recovery device removes moisture from the return air, keeping the condition of the exhaust air stream away from the saturation curve. Frost can either be avoided by either reducing the heat transfer capacity of the energy recovery device, which raises the surface temperature of the heat exchanger, or by preheating or exhaust air or the outdoor air before it enters the device. Another related issue is whether any air can be allowed to leak from the exhaust stream to the supply air stream. In an OA preconditioning application, contaminants that are present in the exhaust air stream may be transferred to the supply air stream. Many types of air-to-air energy recovery devices experience some sort of cross-leakage. This is not often a concern in a mixed air system because most of the air returning from the space is already being recirculated as supply air as it is. Here in Chicago, the mechanical code traditionally required 0% cross-leakage, but that forced the use of fixed plate and sensible recovery devices that were less effective than total energy recovery wheels. So the code has been updated as of 2018 to align with current 90.1 and IACC codes to allow up to 5% leakage with up to class 2 exhaust air, including toilet exhaust. This now makes energy wheels, which are most of which are about 5% or less leakage, a viable design method in compliance with current Chicago mechanical code. One last thing, current IACC code and 90.1 require a minimum of 50% effectiveness of a recovery device. So you need to be careful when using sensible only runaround coils or heat pipes that may be under this threshold. Now that we have a basic understanding of how air-to-air energy recovery is used, let's examine the available technology choices, their performance, advantages, and limitations. For our purposes in this presentation, we'll consider only those technologies that transfer either sensible energy or total, that is sensible plus latent energy. The most common energy recovery devices are coil loops, fixed plate heat exchangers, heat pipes, or rotary heat exchangers, also called wheels. A coil loop, also called a coil runaround loop, consists of 2 or more thin tube coils piped together in a closed loop. A working fluid, typically a solution of glycol and water, is circulated through the 2 coils by a small pump. This is a schematic of a coil loop in an OA preconditioning application. It pre-cools the outdoor air during the summer and preheats it during the winter. Coil loops are typically selected with a sensible effectiveness about 45 to 65% and have an airside static pressure drop that is directly related to the effectiveness of the coil. Now, the positive here is that the coil loops are very flexible. They can transfer heat between multiple airstreams. These airstreams can be physically separated at some distance, which is a huge advantage, particularly in retrofit situations. Also, this physical separation means no cross-contamination, which is a great advantage in laboratories. Now, the capacity of the coil loop is modulated by varying the speed of the pump or using a 3-way mixing valve as shown here. These coils can be selected for the exact amount of heat transfer required, making them very cost-effective. Finally, coil loops package easily inside of a small compact air handler without needs for major modifications. Now, fixed plate heat exchangers are packaged devices that contain alternate layers of plate made of material with high thermal conductivity, like aluminum, for example. The plates are sealed to form separate passages for the 2 crossing airstreams. Sensible heat is transferred between the 2 airstreams through the plates. The direct exchange of heat, i.e. no intermediate heat transfer fluid, gives this technology a relatively high sensible effectiveness, typically 60 to 70%. Now, the pressure drop here is higher. You typically see 0.6 to 1.4 inches of water column throughout this device. Now, capacity modulation is accomplished usually using a phase and bypass damper. The high efficiency plates with sensible recovery have a high frosting potential, again, because it's a sensible only device. It doesn't remove any moisture from that return airstream. So some method of frost protection, a diverting damper preheat is always going to be required when using this in this environment. Now, cross leakage is very low in fixed plate heat exchanger, but not always zero. The better fixed plate designs use a good plate sealing system to minimize leakage between the airstreams, but that's one thing to verify when looking at this technology. A heat pipe looks a lot like a fin tube coil, but the larger individual tubes are separate, sealed, and filled with a heat transfer fluid, typically a refrigerant. A partition divides the heat pipe into separate evaporator and condenser sections. The refrigerant flows between these 2 sections without the need for a compressor or a pump. Heat pipes have an average sensible effectiveness, typically 30 to 55%, depending on the number of rows and tubes and fin spacing. Typical pressure drop ranges from about 0.2 to 0.8. Again, this is a coil. Capacity modulation is accomplished using typically a phase and bypass dampers or varying the tilt angle of the heat pipe itself. Some method of frost protection, whether bypass damper, preheat, whatever it is typically required when the device is used in outdoor air preconditioning applications in cold climate. Another positive aspect of these heat pipes, they allow very little cross-leakage between the streams. But a lot of times the way we see these used actually in supply air tempering applications. So let's take a little bit of a deeper look inside the heat pipe itself. The refrigerant inside the tubes absorb heat from the warm air flowing over the evaporator end of each tube, causing the liquid refrigerant to evaporate. Because the air flowing over the condenser end of the tube is colder than the air flowing over the evaporator end, the vapor pressure of the refrigerant is higher in the evaporator side. This vapor pressure difference causes the refrigerant vapor to migrate from the evaporator end of the tube to the condenser end. The cold air flowing over the condenser end absorbs the heat from the refrigerant vapor, causing the refrigerant to condense back into a liquid. The condensed liquid refrigerant is then wicked back to the evaporator end of the tube to repeat the cycle. The cycle reverses when the relative temperatures of the 2 airstreams switch, so it allows for seamless summer and winter usage. Now, rotary heat exchangers, really common in our industry, consist of a revolving cylinder that contains a matrix of channels to direct air through the wheel. The wheel rotates between the 2 airstreams, with the airstreams configured in a counterflow arrangement. A wheel can transfer sensible heat only or transfer sensible and moisture. A total energy wheel, known as an enthalpy wheel or a passive desiccant wheel, transfers both sensible heat and moisture. As the wheel rotates between the 2 airstreams, it absorbs sensible heat and moisture from the hot, humid airstream and rejects it to the colder, drier airstream. The matrix of a total energy wheel is either made from a fibrous material, such as paper, plastic, or aluminum, with a desiccant material bonded to its surface. Moisture is transferred because the desiccant coating has a strong affinity for water vapor and an enormous internal surface area. In many climates, the ability to transfer moisture is helpful in both cooling and heating seasons. During the cooling season, the transfer of moisture helps dehumidify the air. During the heated season, it helps humidify the air. Capacity modulation is typically accomplished by bypassing a portion of the air around the exhaust side of the wheel. However, some manufacturers recommend varying the rotational speed of the wheel. All wheels exhibit some cross leakage between the exhaust and supply air streams. However, proper placement can help minimize this leakage. Now, like I mentioned just now, leakage between the exhaust and supply streams occurs in all rotary heat exchangers, regardless of their respective designs. Generally, the amount and direction of cross leakage through the seals and matrix is controlled by managing the pressure difference between the supply and exhaust air streams. The configuration of the exhaust and supply fans with respect to the rotary heat exchanger, i.e. blow through versus draw through, affects this pressure difference. The best fan arrangement for a particular application depends on the desired performance characteristics. Now, when it comes to controlling cross leakage via carryover, fan arrangement has no effect. Instead, wheel geometry and rotational speed determine how much the rotary heat exchanger will carry from one airstream to the other. To minimize contamination between the airstreams, some rotary heat exchangers are provided with a purge section. As the wheel rotates, the channels are in a 5 to 10 degree arc pass through this purge section. While there, the channels are flushed with outdoor air that is immediately diverted back to the exhaust airstream. Although the purge section minimizes contaminant carryover into the supply airstream, it does nothing to mitigate leakage through the seals or through the matrix. It also reduces the effectiveness and energy savings associated with the wheel. Without the purge, however, there's no other means to control carryover path of cross leakage between the airstream. Now, that said, most airside energy recovery applications can tolerate a modest amount of cross leakage. In such cases, properly arranged fans and a wheel with an effective sealing system often make this purge section unnecessary. Next, let's talk about integrating these airside energy recovery into familiar systems. So this mixed air VAV system delivers a variable volume of constant temperature air to local VAV terminal units. The VAV air handler includes a flow measuring damper to maintain minimum outdoor airflow, a total energy recovery wheel with both supply and exhaust bypass dampers, a heating coil, and a cooling coil. This air handler supplies cool, constant temperature air to local VAV terminals. When using a mixed air system, there are many climates where the use of an airside economizer can be beneficial for many hours of the year. When the system is operating in the economizer mode, the energy recovery provides no outdoor air preconditioning benefit. In fact, if the energy recovery device is not turned off, it actually adds heat to the supply airstream, increasing the cooling load. Proper economizer operation and integration of the energy recovery device into the system control mode allows you to maximize energy savings and minimize the payback period for the energy recovery device in question. In this application, the air-to-air energy recovery device should be sized for only the minimum outdoor airflow required for ventilation, not for the full supply airflow. Bypass dampers are recommended to enable economizer operation and reduce the airside pressure loss when the energy recovery device is not being used, thus reducing fan energy consumption. So there are 6 different distinct control modes for a mixed air VAV system that uses a total energy wheel to precondition the outdoor air. They can be displayed graphically in a psychrometric chart here. In mode 1, where the outdoor air enthalpy exceeds the return air enthalpy, both bypass dampers are closed and the wheel is operated at full cooling capacity, lowering the enthalpy of the outdoor air as much as possible. The cooling coil is then modulated to maintain the desired supply air dry bulb temperature. The table in the upper left-hand corner of the slide shows the number of hours that an example system will operate in this mode. In each of these 2 locations, notice that Jacksonville, the predominantly cooling climate, spent many more hours than Minneapolis with the wheel operated in this cooling mode. In mode 2, the outdoor enthalpy is lower than the return air enthalpy, so the wheel is turned off. Operating the wheel would increase the enthalpy of the entering outdoor air, adding unwanted cooling load. Both bypass dampers are opened here to save fan energy. The comparative enthalpy economizer will be activated here, also bringing in 100% outdoor air through the bypass damper to handle as much of the cooling load as possible. Any remaining load is handled by the cooling coil. In mode 3, the outdoor dry bulb temperature is lower than the desired supply air temperature. The system remains in economizer mode here, with the outdoor and return air dampers adjusting to maintain the desired supply air temp. The wheel remains off with both bypass dampers open. In this mode, all of the cooling load is handled by the airside economizer, so the cooling coil is also turned off. The key thing to note here is that the wheel system in Jacksonville should be turned off completely for 37% of the total operating hours, and the Minneapolis should be turned off for 43% of the total operating hours. In mode 4, the outdoor air is cold enough so that the outdoor air dampers reaches minimum airflow setting and the economizer is deactivated. The supply side bypass damper is now closed and the exhaust side damper is modulated, varying the wheel heat capacity to avoid overheating the supply air. Again, don't make the mistake of continuously operating the wheel at full capacity here. This would require turning on the cooling coils to recool this overheated air. In mode 5, the outdoor air is so cold that the wheel cannot provide enough heat to reach the desired supply air temperature. Both bypass dampers are closed and the wheel operates at full heating capacity. The supplemental heating coil now has to be turned on to help maintain the desired supply air temperature. Centralizing as much of the exhaust air as possible decreases the number of hours in this wasteful mode, thereby saving all the heating energy you can. Finally, in mode 6, the outdoor air is below the temperature at which the exhaust side of the wheel will frost. This preheat coil is turned on to warm the entering outdoor air above this frost threshold temperature. The wheel operates at full heating capacity, meaning both the sets of the bypass dampers are closed, and the supplemental heating coil helps maintain the desired supply air temp. Alternatively, we could utilize the bypass dampers on the exhaust side or slow down the wheel with a VFD to reduce the energy recovery effectiveness in this zone to avoid the frost condition entirely. Now, important to note, the total hours of wheel operation, either in the cooling or heating mode, are very similar between Jacksonville and Minneapolis. And the reason why we sum these up is just to show that energy recovery is not just for hot, humid climates. It can be very effective no matter where you are in the country. All right, so I want to stop here for questions. I don't know if there's any in the chat or the Q&A feature.
We don't have any questions in the Q&A right now. If anyone has any, please, you can either raise your hand and ask it. I can let you have voice, or you can go ahead and ask it in the Q&A. But as of right now, we're all open.
Well, fair enough. Oh, it looks like one just came in.
Oh, yep.
Can you read that out? I got the PowerPoint on.
Sure. So Randy Stevens asks, what's the typical pressure drop through an energy wheel?
The typical pressure drop through an energy recovery wheel really depends on the size of the wheel. Now, it's really critical. There's a kind of a balance between energy recovery effectiveness and pressure drop. So when you're designing a piece of rooftop or air handling equipment, you can use the smallest wheel possible, which is going to give you the lowest first cost, but it's going to have a very high pressure drop and a low effectiveness. Or you can spend more money on a larger wheel itself and pay more in first cost, and you have a much lower pressure drop and a much better effectiveness. Now, what we've seen is that eventually there's a diminishing rate of return in effectiveness for these wheels, so you can keep getting larger and larger and larger in terms of your wheel, and your effectiveness starts to level off. But the thing that you do continue to gain is a decrease in pressure drop. So continuing to oversize those wheels, even though you don't see as big of a gain in your temperature benefit, you do see a large gain in your pressure drop benefit. Thanks for the question, Randy.
We got another one that came in from Andy Limpera. Question is, an earlier diagram showed that our total enthalpy wheel was being used during economizer mode. Why was that, or did I misunderstand? Seems it looked like it was until the discharge air temp was 55 degrees.
Yep. So that is the mode in which we are using the, there we go. So this one is still off here. Yep. Yep,
he says earlier than this.
Oh, it's earlier than this. So it's not in this chart. So typically, if you had economizer mode running, you wouldn't have a good use for that energy recovery wheel unless you were in the heating dominant season. And even then, I really don't think that it would be a good use of fan energy to be using that energy wheel, because often, even in the heating season, you would then overheat that supply air temperature, and you'd need more mechanical cooling to cool it down. So typically when you're in economizer mode, you wouldn't be using that wheel at all. So I apologize if there was a discrepancy in the earlier slides.
Great. Got another one from Virginia Wilson. What are the maintenance differences between a plate heat exchanger and a wheel?
Yeah, great question. Great question. So naturally, one of the big things with wheels is that there's a motor that has to drive it. So you have motors, belts, shivs, things like that to maintain on a wheel. With a flat plate heat exchanger, you don't have any of those items to maintain. You just have damper actuators. The wheels also have to be maintained a little bit more. You have to kind of vacuum them off, for the lack of a better term. Whereas a lot of plate frame heat exchangers, depending on the application, you can just spray down. Now, it's interesting with plate and frame heat exchangers, a lot of times that their method of use dictates a higher level of maintenance items to be required, because usually when you see a plate and frame heat exchanger, it's coming out of some sort of like a diesel shop, so sort of an automotive maintenance facility, something with a lot of nasty contaminants in the air that you end up having to clean off more frequently from that plate exchanger. So it's not necessarily the plate exchanger's fault that you have to clean it more often, but usually in the applications where you use plate exchangers, you end up having a little bit more of a rigorous maintenance schedule.
Great. Another one from Bill Paschal is how to factor the cost and energy utilization of supplementary electric heat, for example, in Chicago.
Now, that is a great question, and one that I think is frequently misunderstood. So when you have, I'm going to go to a good psych chart example here. And so, I mean, traditionally one would think that, hey, why would I ever want to use OA preheat? Why would I ever want to use OA preheat and put energy into a system when I'm trying to recover energy? Isn't that counterproductive to what I'm trying to do? And so what is often misunderstood about that is that by using an OA preheat system in these energy recovery applications, you actually allow the wheel to operate at during a significantly higher number of hours throughout the year. And the amount of BTUs that you need to put in to, again, get that OA from the entering condition to be on the frost threshold condition is not bringing that air up to 32. The frost threshold is often maybe 5 degrees. Again, you're stealing a lot of moisture from that return airstream and dumping it into the OA stream with a total energy recovery wheel. So your frost threshold could be anywhere between 0 and 10. So you're only really preheating from, again, our design is -10 up to maybe 5, 10, 15 degrees on a conservative design. You're not bringing it all the way up to 32. So often the energy balance dictates that OA preheat will actually save you energy, even though you're dumping energy into that, because you allow the wheel to operate for a lot more hours of the year. But not a lot of designs have it. It's very interesting.
Similarly, this is a question for me actually, is as you're looking at reducing your cooling and heating load, like you say, you are increasing your fan power.
Yep.
And as you're getting into some cooling systems that may be highly efficient, how do you determine that break point where, this increase in fan power is more energy use than really you might be using for cooling or heating?
Yeah, and it's a great question. And I think any good energy recovery design, whether you're talking about airside energy recovery and adding some sort of a widget, or if you're talking about waterside heat recovery, really good due diligence needs to be done on the designers on using a good energy and economic software. There's plenty out there on the market. I won't plug any for my company or anything like that, but there's a lot of good software out there that you can use to model different designs and different iterations. And truly energy modeling is going to be required, because your building envelope is going to come into play when you're calculating that out. What's the exact balance point in terms of percent of OA? It's really building to building, case to case.
Great. All right, we've got 2 more, and then I think we're going to let you move on so we can get done on time. From William Kuzan is economizer mode is when the OA enthalpy is lower than the return enthalpy. Can you qualify when the wheel should be used other than just a minimum OA set point?
So the wheel, so again, our use cases of that wheel itself, where's my use cases here. So again, we're going to use it in our cooling dominant mode. We are going to use it in we're not going to use it at all really during this mode here, because the operation of the wheel would increase the enthalpy of the OA. This again is the wheel remaining off. So really it's just zone 1, zone 4, zone 5, and zone 6 are the only times you're going to be operating this wheel. So yeah, when you're in full economizer mode, yeah, you wouldn't be using the wheel. And you say there was one more question?
Right, from Tyler Corey, with winter energy recovery, is it still recommended to have freeze protection if you have water coils? I assume this is after the energy recovery device.
Yeah, it's still recommended to have freeze protection there. Worst case scenario, let's say a wheel motor breaks or the wheel is taken out of commission by a local maintenance staff that doesn't really understand why it's there, it's definitely smart to have freeze protection in that first heating coil, and at a minimum, making sure that heating coil, that heating coil is still a 2-row coil at least, even though it doesn't need it. You're only heating now from maybe 40 degrees, up to 55. It's still good to upsize that coil and implement freeze protection methods that you're used to doing.
All right, thanks everyone for the questions. Move on to the second half.
Sweet. Halftime's over. Thanks for the questions, everybody. All right, so going into waterside heat recovery, why would we be interested in waterside heat recovery at all? The first reason may be strictly practical. In order to efficiently recover heat in the water loop, there must be cooling and heating loads, preferably occurring simultaneously. So, if you have simultaneous heating and cooling loads, it's kind of automatically a great application for it. Next, rather than paying to reject heat, we can recover that heat. This gives us kind of a double benefit. Reducing the heat, recovered heat reduces this heating load that we have in the building, but it also reduces the ancillary power necessary to reject the heat from the cooling plant, thereby also reducing energy costs on that side. Now, some building owners perform energy recovery, which may include heat recovery, not only to reduce operating costs, but also to reduce emissions to the environment. Now, reducing those emissions may be beneficial for a variety of reasons, including recovering heat to satisfy future loads without the need to burn additional fossil fuels. Additionally, specific building owners or local code officials may decide to mandate its use. Now, heat recovery, this kind of gets back to the topic of the energy model that you just brought up. But heat recovery may or may not be justified for a particular application, and often its success is predicated on heating and cooling loads occurring simultaneously on enough hours to warrant heat recovery being implemented. For example, heat recovery may cost more to operate than a separate heating source. For example, a small heating load that has occurred on cool, dry days, let's say the chiller on these days could operate at 60 degrees entering condenser water temperature with no cooling tower fans operating. At this point, the chilled water system operates extremely efficiently. An alternative, on this same day, you could operate the chiller to produce 115 degree water leaving the condenser. Now, that would take considerably more chiller energy to accomplish. So if the amount or cost of heat recovered is less than the additional chiller energy, this condition is not going to be conducive to using heat recovery. And really an accurate analysis of heat recovery systems is critical. You got to account for the simultaneous and heating and cooling loads. That's a really imperative item. And then you really have to do a robust energy analysis on the building prior to implementation to assure that it's a smart financial decision for the end user. Now, the code implications of heat recovery there's not a lot of applications where you're going to be mandated into this thing. And really ASHRAE 90.1 dictates if the facility operates 24 hours a day and the heat rejection exceeds 6 million BTUs and the design service water heating load exceeds 1 million BTUs, then you need a heat recovery system of 60% of the design heat rejection or preheat the peak service hot water draw to 85 degrees. Now, where are you really going to see this? Healthcare facilities, dormitories, hotels, or condos are sometimes the places that you can see them. Now, there's some exceptions to this rule that are shown on the bottom. I don't like reading directly off my slides, so I think everyone can see those there. Just an interesting one to know is that facilities that produce 60% of their service water heat from on-site solar energy or site recovered energy from other sources are exempt for this rule. So if you have some sort of a solar collector system on the roof, you do not need to comply with this regulation. Now, now we have a kind of a general understanding of where we might use this. Let's look at some common usage in the building. Now, service water is defined as the hot water used for domestic or commercial purposes other than space heating and process requirements. In the code portion of this presentation, recall that ASHRAE 90.1 requires service water to be preheated to 85 degrees Fahrenheit, given the other conditions that were called out. Now, this temperature is high enough for most applications found in commercial and institutional facilities, but some process applications may require higher temperatures. In those applications, special compressors and condenser shells may be required. As you can see here, there's heat recovery even available up to 150 plus degrees that you can get off of some machines. But again, you need to take into account the increase in energy you're putting on the chiller in order to create those high temperatures. Within an industrial or commercial setting, there's often a need for heat in many reasons. Some reasons are made in an industrial setting are to make materials more malleable, to keep a product in a specific condition while it cures, and so forth. Quite often, these process loads require constant or near constant temperature. In these cases, the use of positive displacement chillers or centrifugal chillers with small heat exchangers satisfies the need. Now, there's about as many heat recovery uses as there are heating needs throughout a building. Many manufacturing processes must be cooled, with this cooling referred to as a process load. Quite often, these process loads remain constant throughout the year, so you'll have an unlimited supply of heat rejection to heat the building itself. Now, many commercial facilities use water for washing, showering, and other everyday usage. Such facilities include hospitals, for like laundry, showers, sterilization, dormitories for, again, laundry, showers, general use, and hotels. Pool heat is a good example of this. But all of these facilities require large quantities of makeup water that must be heated. So an auxiliary condenser, which I'm going to discuss later in this presentation, may be able to meet these loads. Now, be aware that heating potable or drinking water may bring other requirements. When using positive displacement chillers, where the refrigerant pressure is higher than the water pressure, an additional heat exchanger must be used to isolate the refrigerant from the service water. For chillers in which the water pressure is greater than the refrigerant pressure, let's say in a low pressure centrifugal, using a heat exchanger is still advisable and may be required by local code. Another application for waterside heat recovery is for tempering air in VAV applications. In most applications with multi-zone VAV, each VAV terminal has a minimum airflow setting that usually represents the ventilation requirements for the space. At some point, the sensible cooling load in the space becomes small enough that the required supply airflow is less than the minimum airflow of the VAV terminal. Overcooling can be avoided by tempering the supply air when it diminishes the minimum airflow setting of the VAV. Tempering moderates the cooling effect by adding sensible heat to the supply air, either at the VA terminal or within the space itself. The amount of heating energy required for this task is usually minimal, and many heating loads can be met with low water temperatures, even 105 degrees or lower, because the heat recovery from the heat really needed for this tempering is minimal in itself. Now, this is an ideal application for heat recovery because any chiller will be able to handle this increase in lift. Now, heat recovery can be benefit systems with both large and small ventilation loads. It doesn't need to be a huge OA application for you to use the heat recovery, but let's say you do. For these large OA loads, warming outdoor air generally requires a significant amount of heat. In many process applications, there's a constant cooling load. The heat that would otherwise be rejected to a cooling tower can be used in this case to heat or preheat at least the outdoor air. This may also be beneficial in comfort cooling applications where there's no airside economizer. In such cases, interior spaces often require cooling, whether there's an outdoor air heating load. Now, for very small OA loads, when there's small amounts of outdoor air being treated, the use of a small water-to-water heat pump may be beneficial. The evaporator portion of the heat pump can pre-cool return chilled water, and the condenser side can reject heat to a separate water loop used to preheat the outdoor airstream. Now, let's look at some basics of heat recovery in the chiller itself. We'll look at some how a system might be put together and capabilities of various compressor types. So heat recovery generally uses less total energy than separate heating and cooling sources and always reduces the amount of heat that must be rejected. One drawback is that it often requires more chiller energy than a cooling-only chiller because the chiller operates at an elevated condensing pressure and temperature. If the increase in the chiller energy is greater than the amount of useful heat recovered, the system uses more total energy. This, however, is seldom the case. When applying heat recovery, it is important to understand that the different compressor types respond in different ways to different condensing conditions. Positive displacement compressors, such as scroll, helical rotary, or reciprocating compressors, react to condenser pressure differently than centrifugal compressors do. This figure here shows a generic single condenser chiller used to satisfy cooling loads. The heat is transferred from the cooling load to the chiller to the condenser, and then finally to the cooling tower that rejects the heat to the ambient condition. Now, a standard chiller with no extra shells that are required can be used in a heat recovery application. This works well when a heating load exceeds the cooling load of the chiller during most of the operating hours. This is more likely the case with process loads than with comfort cooling loads. A single condenser chiller is a good match in systems with year-round cooling and heating loads. Most standard water-cooled chillers can provide suitable condenser water temperatures for heat recovery if operated at even slightly elevated refrigerant condensing temperatures. Now, recirculating the same condenser water through the hot water coil of an air handler in an open cooling tower increases potential for tube fouling. Adding a separate water loop, another pump, and a plate and frame heat exchanger, as shown here, can eliminate this risk. One loop circulates water through the chiller condenser, the plate and frame heat exchanger, and hot water coil. The other loop circulates water through the plate and frame heat exchanger and the open cooling tower. In this configuration, it's important to note that the heat exchanger must be sized for the total heat rejection load of the chiller in case the chiller is fully loaded and there's no heating requirement available. Now, there are some chillers, usually centrifugals, that have two separate condensers, one that rejects heat to the cooling tower, the standard condenser, and the other that interfaces with the heating load. Let's look specifically at three different types of heat recovery chillers of this type. So the dual condenser or double bundle heat recovery chiller contains a second full-size condenser that serves a separate hot water loop. It is capable of significant heat rejection and relatively high leaving water temperatures. This chiller can also operate as a cooling-only chiller at normal condensing temperature. This type of chiller allows the amount of rejected heat to be controlled, although chiller efficiency is sacrificed for higher hot water temperatures. Now, control of this system is basically accomplished by varying water flow through the standard condenser. Reducing flow through the standard condenser causes the chiller condenser pressure to rise, thus allowing the leaving water temperature of the heat recovery condenser to become elevated. Conversely, as the water flow rate through the standard condenser is increased, the condenser pressure drops and the heat recovery leaving water temperature decreases. An auxiliary condenser system, in the auxiliary condenser system, the heat recovery chiller makes use of a second, smaller heat recovery condenser. Now, it's not capable of recovering as much heat as the dual condenser full capacity chiller, but because of the leaving water temperatures for this chiller are also lower, let's say they're more standard around 95 degrees, the auxiliary condenser is typically used to preheat water. Now, this condenser requires no additional controls and actually improves chiller efficiency because you're condensing at a lower condensing pressure. Now, when this auxiliary condenser is used, the amount of heat recovered is not controlled at all. The heat transfers from the refrigerant to the heat recovery water, and you kind of get what you get. Now, this slide here gives a good comparison of single condenser, dual condenser, called same size, and auxiliary condenser attributes. So the amount of work a compressor must perform is proportional to the pressure difference between the evaporator and condenser. This is often referred to as the lift. An elevated temperature used for heat recovery, the condenser pressure also rises. Depending on the compressor type, either positive displacement or centrifugal, the compressor reacts differently to this change in lift. So here's everyone's favorite chart, the pH chart. The theoretical vapor compression refrigeration cycle for a helical rotary water chiller can be plotted on this pH chart as shown here. But when heat recovery is performed at an elevated temperature, the condenser temperature and pressure rise. This causes the compressor to perform more work for a given cooling load. Now, a positive displacement compressor selected to meet a specific cooling load will operate at the given temperature and pressures, and the chiller will provide chilled water and warm condenser water. However, as the condenser entering and leaving water temperature rise, the capacity of the positive displacement chiller is reduced. In addition to this capacity reduction, the power necessary to provide compressor lift increases. A positive displacement compressor selected to meet a specific cooling load will operate at the given temperature and pressures, and the chiller will provide chilled water and warm condenser water. However, as the condenser entering and leaving water temperature rise, the capacity of the positive displacement compressor is reduced. In addition to the capacity reduction, the power necessary to provide the compressor lift increases. Although the chiller can operate in heat recovery mode, one should analyze whether the additional power required and the reduction in capacity warrant the benefit. This slide shows generically how two positive displacement compressor technologies react to elevating condenser temperatures and pressures. Because both power and capacity are changing, the power draw is shown in units of kW per ton. Now, this slide shows an example of how a centrifugal's chiller efficiency changes depending on the duty, cooling only or heat recovery. When selected for cooling only, the chiller, in this case, achieves a efficiency of 0.57 kW per ton of full load. Since the impeller design is optimized for normal cooling performance, i.e. 95-ish degree leaving condenser water temperature, it is unlikely that the chiller can make elevated leaving condenser water temperatures of 105 or above. So to produce condenser water temperatures of 105 or above, the chiller's compressor must be changed. This results in a higher kW per ton of the heat recovery temperature, which is expected. However, when the chiller is selected for heat recovery, operates in a cooling only mode, you're going to see a higher kW per ton, as its impeller itself is optimized for the heat recovery condition, not the cooling mode condition. Now, when using a centrifugal chiller in a heat recovery application, it's extremely important to understand the compressor's part load operation. The larger pressure differentials required for heat recovery design also tend to reduce the unloading capability of the compressor itself. Consider a given diameter compressor impeller that rotates at a constant speed. As the load on the chiller decreases, the flow rate of a refrigerant through the compressor drops. Radial velocity, which is proportional to the refrigerant flow, decreases as well. Even though the speed of the rotation and the diameter of the impeller are constant in this case, the tangential velocity, which is proportional to the product of impeller rotational speed and impeller diameter, drops because the pre-swirling refrigerant caused by inlet guide vanes. Now, the result is a shorter resultant velocity vector, shown here as R, which means that less static pressure is generated by the compressor. Now, as the load and the corresponding refrigerant flow continue to fall, at some point, the radial force becomes smaller than the generated static pressure, letting the pressurized refrigerant vapor flow backwards from the diffuser passages into the impeller itself. Now, this instantaneously reduces the pressure within the passages to lessen the radial force, and the compressor is able to reestablish the proper direction of refrigerant flow. Now, this condition shown here is known as surge. Now, as long as this unstable load condition exists, the refrigerant alternatively flows backwards and forwards through the compressor, generating a lot of noise and vibration, which anyone who has heard it knows that the chiller is not very happy in this condition. Prolonged surging is not good for any compressor and really should be avoided. So in summary, a positive displacement chiller can operate well in a system controlled with either entering or leaving condenser water temperature. Although if operated with a constant leaving condenser water temperature, the capacity will be reduced and the power will be increased. Centrifugal compressor chillers should be operated with reduced entering condenser water temperatures at part load conditions. This will reduce the likelihood of surge. Now, many chilled water systems are configured in the traditional primary-secondary decoupled arrangement. This may not be optimal for performing heat recovery operation. The simple reason for this is that all operating chillers are loaded to equal percentages. The amount of heat recovery available is limited by chiller loading. For the same building load, the load on each chiller can be significantly different. It depends on the chilled water system configuration. This section next that we're going to talk about discusses the advantages of various systems, configurations, and specifically with respect to heat recovery. So as I said, we're going to examine now the different configuration options to determine their applicability to the system heating requirements. Now, again, like we showed before, the traditional primary-secondary arrangement resulting conditions are shown here just for reference. Again, 1890 MBH of available heat, about 110 MBH of auxiliary heat required to meet the loads. Now, if we move one chiller to the load side of the bypass line here, it is going to be loaded preferentially because it always receives the warmest return water temperature. Therefore, when operating, it rejects as much heat as possible. The chiller pipe in this location also adds to the chiller plant flow rate and does not reduce the return water temperature to the other chillers. If the system supply water temperature is maintained, the chiller may reject more heat than can be used by the heating load. This calculation shows that the heat recovery chiller can produce more heat than the amount required. The excess of 400 MBH must be rejected in this case to the towers. Now, if we look at a side stream case, a chiller piped in a side stream position as shown here can be loaded to any load condition by varying its chill water set point. The chiller is piped in parallel have a flow rate greater than those in traditional primary-secondary systems because the side stream pump does not help satisfy the system chilled water flow requirements. Now, this is because the side stream chiller pre-cools the water, and these chillers have an entering water temperature lower than the temperature of the water from the cooling coils in the system. Now, the cooling only chillers must be selected for the design delta T, even though they will experience a reduced delta T whenever the heat recovery chiller is running. It is possible that both cooling only chillers may be required to run in order to meet secondary flow requirements, even if only one chiller is required to satisfy the load. Now, an advantage of the side stream configuration is that the side stream chiller does not need to produce the design system supply water temperature. It can produce whatever water temperature is necessary to exactly meet the required heating load. This allows the cooling to be produced at a higher chilled water temperature, resulting in more efficient operation for this particular chiller. Because the heat recovery chiller is controlled to only provide the amount of heat required, there may be no need for this chiller to be connected to a cooling tower. This allows a single condenser chiller to be used in this position without the need for a separate heat exchanger. Now, two possible control strategies are available for side stream loading. The first is simply to load the chiller enough to satisfy the heating requirements. The second, for positive displacement chillers, is to load the chiller enough to produce a specific condenser water leaving temperature. So here's a summary of the system conditions for the three configurations we just mentioned. The negative auxiliary heat required shows that the heat recovery chillers ran at a higher capacity than necessary to satisfy the heating load. This is not necessarily a disadvantage when compared with the primary-secondary configuration because the heat must be rejected whether it is from the cooling-only chiller or the heat recovery chiller. A variation of the side stream configuration can be referred to as distributed side stream. Now, here's an example of it. So the air handlers, let's say in this case, there's a big central chilled water plant but the air handlers are remote from the central chilled water plant, in a different part of the building. So let's say there are tempering requirements necessary at a few of these air handlers. Basically, recovering heat at the central plant and piping it to those air handlers is not cost justified. Now, in some cases, putting a small chiller or heat pump in the fan, air handler mechanical room may satisfy the job requirements here. In such an application, the chiller is sized for the heating requirements only, and small heating and cooling pumps are installed in the fan room. The heat recovery chiller is then in the side stream location and located where the heat is. And then again, basically pre-cools a lot of that chilled water that goes back to the central plant. Now, some designers feel that variable primary flow system configuration here provides a method to load a specific chiller. Now, this can be done when the heat recovery chiller is the only chiller activated. However, when a heat recovery chiller and a cooling only chiller are both active, it becomes extremely difficult to preferentially load the heat recovery chiller. Unimpeded, basically the water flows are going to balance and are dependent on the evaporator pressure drops. If the pressure drops are equal, the chillers are loaded at equal percentages. Systems that have chillers in parallel and which attempt to load the heat recovery chillers using variable flow are unlikely to work well. But one may attempt to modulate the valves to achieve preferential loading, but this is not a simple thing to do. Now, alternatively, dedicated pumps may make it simpler to operate a VPF system with different size chillers. However, all pumps will need to operate to produce the same pressure, so they will run at close to the same speed and flow rates will be proportional to design. Again, one may attempt to modulate valves to achieve preferential loading in this case, but again, not a simple thing to do. A possible method for loading a chiller preferentially is to install it in a side stream location and vary the water flow. When varying the water flow, heat recovery capacity control must be accomplished by changing the pump speed rather than adjusting the chilled water set point. While this is theoretically possible, maintaining constant flow through that side stream chiller and changing the set point is simpler. The chiller also operates more efficiently at higher evaporating and leaving water temperatures. Now, to summarize our water source heat recovery discussion, basically heat recovery from chiller condensers can be used to provide an economical source of heat for comfort conditioning, domestic hot water, and process loads. By properly applying and controlling the heat recovery chiller in the system, these benefits of reduced operating costs, reduced emissions, and wide uses of energy use in the site can be realized. Now, during the analysis phase, it's really key to determine if heating loads are going to be occurring simultaneous with cooling loads throughout the year, and we need to analyze the financial and environmental benefits to make sure they actually meet the owner's criteria. During chiller selection and operation, we need to make sure we select the chiller for the heating requirement, use the appropriate system configuration, and design the system, including controls. Ideally, you keep the system simple. Control the system properly by having an actual integrated BAS, and accrue the benefits of reduced operating costs, emissions, and tower water usage throughout the life of the system. Bonus topic number 1, water source heat pumps. We're done with the water thing. I'm just going to run through these 2 bonus topics, and then we'll have time for questions. So in a traditional water source heat pump system, all of the heat pumps are connected to a common water loop. A cooling tower and hot water boilers are also installed in this loop to maintain the temperature of the water within the desired range. At many times of the year, some heat pumps in the building may operate in the cooling mode, while others operate simultaneously in the heating mode. As an example, during the fall season, some interior zones may require cooling, while the perimeter zones require heating. The heat rejected the water loop by the heat pumps that are operating in the cooling mode keeps the temperature of the water loop relatively constant. During these times, both the cooling tower and boiler can be shut off, thereby saving energy. Similarly to the water source heat pump example on the previous slide, VRF systems can take advantage of zones that require simultaneous heating and cooling to basically condense refrigerant directly in the heating zone as opposed to the condensing unit. It is important to note that with many manufacturers, ambient temperature loading limits exist that limit the time the system can spend in these simultaneous heating and cooling modes. With that, we got 2 minutes for questions.
Hey everybody, just as questions start to roll in, I wanted to bring up, if you are looking for your PDH credits for this, you'll need to email Don Doherty at administrator@illinoisashrae.org and request them directly from him. So just a heads up for everybody.
You want to help me with reading off questions?
Sure, it looks, well, right now we're still waiting on questions. We have one from the last round saying any special wheel considerations for 100% OA systems.
Frost control, 100%. That's going to be the big one for any big OA systems. The wheel size in itself is going to become very simple in that case because the supply air flow equals the OA flow, which is going to equal your nominal wheel flow. But when you have that much OA going through the system again, the key is to centralize as much of the exhaust as possible. If you don't have a lot of exhaust coming back to that 100% OA unit, you're going to spend a lot more time in frost or spend a lot more energy trying to preheat.
All right, any other questions, please send them in. We've got one saying you mentioned 150-degree temps can be reached. How high? I assume these were screws.
Yes, yeah, that is a screw example. So, I mean, you can get 150, almost 160 off of a screw chiller. But again, the key thought is, are you using more energy to operate the chiller at that lift position rather than just using, are you actually gaining anything by doing that is really the question. Now, if we're talking about a net zero facility and we just need that temperature of water, we just need that temperature of water and we can't use fossil fuels. So that may be justified. But in many cases, if we're just looking at a simple cost balance between, using fossil fuels to burn, to create, hot water, and using a chiller to do so, it's not, in many cases, not going to be cost advantageous to create 180 or not 180, but 150 plus degree water with a chiller, although it can be done.
A particular person named Blueberry Yum Yum asked the question, any considerations on air-cooled free cooling chillers?
Yeah, air-cooled free cooling chillers is it's a great application. Basically, it takes a dry cooler and a chiller and it makes a nice HVAC sandwich. Basically, what you do is you take 2 water coils and you strap them on the side of an air-cooled chiller, and you take advantage of the condenser fans that already exist on that machine to run cold ambient air over those water coils, and you send your actual water that you're using throughout your facility for your air handler cooling coils, or maybe it's separated by a loop and a plate and frame heat exchanger to those coils out there to basically get cooled down by the ambient air temperature as opposed to having to use mechanical cooling. Great application and something that I think people should start taking advantage of more.
Great. At that point, I don't see any more questions coming in. Another minute or so.
Thank you very much for the time, everyone. I really hope everyone learned something today, and it's a good topic, and I hope everyone took notes. So, I guess have a great rest of your week.